Okay, right. So the first point in the module 2 is a kernel maps. So kernel map minimization, minimum forms of switching functions, 2 and 3 variable kernel maps, 4 variable kernel maps. Different types of kernel maps are there. But directly going for this kernel map may be quite complex. Before this, we should understand some of the basic rules of Boolean algebra. Okay, I think in the first semester you have come across Boolean algebra as well as the rules. Okay, so for to go to this kernel of maps, first we will see what are all the Boolean algebra rules are there, and then we will move on. Okay, so basically, what is this Boolean algebra? So algebra, it is also a mathematical term, right? So the Boolean algebra or a switching algebra, it is also called as a switching algebra. So it is a simple system where a mathematical logic, it is providing a mathematical logic to perform different mathematical operations on a binary system. See, when I say binary system, definitely we have all come across binary number system. Okay, 0 and 1. So that is very much important. And in the beginning classes also, I have discussed regarding this, right? I We have discussed on number systems like decimal number system, hexadecimal number system, octal number system, or binary number system. So here a binary number system is an approach to solve a mathematical logic operations. Okay, then what are these binary number system? These are only two elements. Definitely we know that 1 and 0. Okay, so by which all mathematical operations are to be performed. Based upon 1 and 0, we are going to perform other logical mathematic operations. Okay, see, you have to understand one thing from this Boolean algebra is logical understanding, logical mathematics. Okay, logical mathematics. So here, uh, these 1 and 0 are used for mathematical operations. Okay, then on what are the operations? When I say mathematical operations, it will be a decimal operation. It will be a plus, minus, uh, multiplication, and division. A basic four things are there. Likewise, in a binary number system, there are mainly three operations are there. That is AND operation, OR operation, NOT operation. Okay. I know you have all come across through these logic gates, right? AND gate, OR gate, and NOT gate. So through these operations, AND operation, OR operation, NOT operation. So we can a simple and complex binary mathematic operations can be solved by using these basic three operations. Okay, so there are many other rules are there that we will see which are the rules are applied by using these three operations. Okay, now here some basic rules, basic logical Boolean operation. Okay, we know that the basic AND operation where a product form or multiplication, in a decimal we call it as a multiplication, but here it is called as a product form. Okay, the Multiplication here it is denoted as along with the dot. If I put a dot, it means it is showing a AND operation or product operation. Okay, so when I go for AND operation, when I have a number of inputs, which are called as variables, here the AND operation is performed on 2 bits. Say there are two input variables, for example A and B. These are two input variables. And what will be the output for this? It will be a C. Let us consider these are the variables. So here, what are the different uh, combinations of these two inputs? It is 0, 0, 0, 1, 1, 0, 1, 1. So in between these two inputs, if I perform a dot function, if I perform a dot function or a product function or an AND function, what will be the result? Is obviously 0 into 0 is always a 0, 0 into 1 is a 0, 1 into 0 is again a 0, and 1 into 1 is 1, right? That is what the operation we will get from, the result we will get from the AND operation. So here, when I go for OR operation, it is 0 plus 0. OR operation is addition, but it is not a simple addition like a decimal number in a decimal number system what we use, but it is Boolean OR operation, addition. So what is the output of this function is 0 plus 0 is 0, okay, 0 plus 1 is 1, 1 plus 0 is again 1, and 1 plus 1 is always 1, right? There is no 2 because 1 plus 1 is 2 in a decimal, but in a binary we don't have a 2 number, right? We have to represent it by 1 0, but this is a logic function. This is a logic function, so 1 plus 1 is equal to 1. Okay, so this is an OR function. Likewise, if I go for a NOT operation, whereas one bar or complementary, right? So the complement of 1 is equal to 0 and the complement of 0 is equal to 1. It is a NOT operation. Whatever the input is there, we will get the opposite of that as an output. Okay, again there are only two logics are there, 1 and 0. If the input is 1, the output will be opposite to that, that is 0. If the input is 0, the output will be 1, right? And even we know the uh, logic symbol of AND gate, how it is like this, right? This is an AND gate, whereas two inputs are there, A and B. This is the logic symbol for this operation, okay, which is going to make A into B as an output. So which is called as C equal to A into B. Okay. So for OR operation, what is the logic symbol? It is like this. Okay. A and B are two variable inputs which can be 0 0, 0 1, 1 0, or 1 1. Here it is dot product. Here it is plus product. Output will be A plus B. That is C equal to A plus B. And when I go for a NOT gate, simple input one, only one input is there for NOT gate, and there will be a bubble here, and then directly output. The input is A and output equal to C equal to A bar. Okay, so these are a simple basic logic functions of Boolean algebra. Hope you are understanding. I'll go for the next point now. These are main essential parts that we should know before going for Karnaugh maps, K-map, before starting the second module. Okay, now here, there are some basic rules of binary variables and constants. Okay, that we will see here. Let us assume the A is either 0 or 1. Okay, by considering these products, see A is a variable now, and 0 and 1, these are constant numbers. Okay, now here I am combining the variable with the constant number here. Okay, so what will be the rule that I will get from this? A into 0, that is AND operation. A may be 0 or 1, but the second variable is a constant here. Second number is a constant number here, which is 0. So anything into 0 is always 0. This is the AND operation that we have seen up here, right? See, anything into 0 is 0. If any one of the input is 0, the output is 0. That is the AND operation. So this is one rule. And again, A dot 1 equal to A. That is anything into 1 will be the same number which is the first variable, A only. If A is 0, let us take an example for this. Okay, if A is 0 dot the constant number is 1, what will be the result? It will be 0.
0.
If A is 1 and the constant number is 1, what will be the result? It will be the 1, this one. Here it is, this one. Okay, say for an example, if I draw the logic symbol for this function, this operation, this is the AND gate, where one input will be 1, another input will be A. So for this, always the output will be A, right? Hope you are understanding. You can reply in the chat box if you are not understanding, if you have any doubts. Okay, then uh, okay, the third rule here. Okay, understanding. Good. A plus 0. Here, A plus 0 is always A. See, A dot 1. Here it is a AND function. The output is A. A plus 0. The function is OR function. The output is always A. The only difference between this is AND function, this is OR function, and the constant number here is 1 and the constant number here it is 0. Okay, so if we want to prove this also, it is quite easy. A, this is A, this is 0, and this is OR function. What will be the output? It is A. How come? See, if A is 0, 0 plus 0 is 0. If A is 1, 1 plus 0 is 1. So whatever A I am putting here, giving here or applying, the same thing I am getting here. 0 to 0, 1 to 1. Okay, so that is why A plus 0 is equal to A, right? Then a plus 1 equal to 1, right? Uh, right, I think the rules you have understood. A plus 1 is equal to 1. A may be 0 or 1. If the constant number is 1, the output will always be 1. If I go to here, see, if in this OR operation, if one input is high, the output is always high, right? Whether it may be the another input may be 0 or 1, the output is always high whenever any one of the input is high. So here always one input is always high, so definitely we will get the output as high, always one only, whether the a may be 0 or 1. 0 plus 1 is 1, 1 plus 1 is 1. Then a plus a bar, see here it is a not gate. Now a plus a bar is always 1. How come it is possible? Let us see. A plus a bar, right? Now what I will do is, this is a, this is a bar. There are two inputs, 0. If a is 0, what will be the a bar? It will be 1. So a plus a bar, 0 plus 1 is always 1. Now if I take a as 1, what will be the a bar? It is 0. So what is the result? It is 1 plus 0 is always 1. So a plus a bar is always 1. Okay. Then a dot a bar is always 0. Here it is a AND function. A dot a bar is equal to 0, always 0. How come it is possible? Let us consider a. If a is 0, a bar is 1. 1 into 0 is 0. If a is 1, a bar will be always 0. Then 1 into 0 is always 0. So always we will get the output as 0 whenever a dot a bar happens. Okay. These are the main important rules that you should know, all of you, or through whole your life also. It will be helpful. Okay. Then after this, a few laws are there. Boolean laws are there. Boolean algebra laws. We should go through that also, which are much important during solving a Boolean expressions. Okay. Now, equivalence law. It is so simple. Equivalence law, where let us consider x is a set of 0 and 1. Okay. 0 and 1 is the set of x. Then y belongs to x. If I say y belongs to x, then y is also containing the same numbers, which is called as equivalence law. If x is 0, y is also 0. If x is 1, y is also 1. Both variables are equal, are having the same content, so I can say that they are equivalent, and I can apply the equivalence law. Okay, so when I say x is equivalent to y, then whatever the value x is holding, the same value will be held by the y variable. Then a complement law for Boolean algebra. It is nothing but a not operation, right? A bar, uh, a, if input is a, the output will be a bar, right? If 0 bar, it means the output will be 1. If 1 bar, the output will be 0, right? So if a is equal to 1, then a bar equal to 0. It is a complement. If a equal to 0, the complement of a is 1. Correct? It's just a simple not gate or not function, complement function. Then identity law, where see here in identity law, a dot x and a plus x, two rules are there. Always the output is same as one of the input, right? Here output is a, here also the output is a, whereas it is being compared with the a dot x or a plus x. Now a can be either 0 or 1. A can be either 0 or 1. But the only thing is the x. What would be the x? To get output as a in the AND function, the x should be 1. The x should be 1. And in the OR function, the x should be 0. Okay. So let us see how it is. Let us prove how this is going to happen. Right. Now, what is a condition that for identity law? The x should be 1 for AND gate. The x should be 1 for AND gate and 0 for OR gate. Okay. Let us see how it is possible. Now, I will write a here. I will write x here. Okay. The output, how the output we will get. Say this is 0, this is 1. Now let us take the first condition. The x is always 1 for AND operation. Now let us do AND operation. 0 dot and 1 dot. This x should be 1 for AND operation. I will write 1 here and 1 here. What will be the output? 0 dot 1 is 0, 1 dot 1 is 1. So what I am getting here, whatever the input A is there, that is reflecting at the output side, right? But what about this x variable? It is always 1. So for AND operation, the x should always be 1, and for OR operation, the x should always be 0. Let us see now. I'll make this as 0 now, and instead of dot, I'll make it plus. Now 0 plus 0, it is 0. 1 plus 0, it is again 1. So whatever the input A is there, that is reflecting at the output side. So this is identity law. I'm identifying the A and the same thing is being reflected at the output side. Okay, but the condition is what? The x should always be 1 for AND operation and should always be 0 for OR operation. Okay. Then commutative law, or also a cumulative law for Boolean algebra. So it is so simple. Let us take any kind of any number of variables, 3 variable, 4 variable, or 2 variable. The only arrangement of these variables can be any position. Say like a plus b plus c is equal to a plus c plus b. The position does not matter in these kind of expression. Such arrangements can be said as cumulative law, right? The ABC can be written as BCA. Like here, one my example is there by taking a 2 variable. One is a plus b is equal to b plus a. Now the position has been changed, but the result will not change. They remain same. A dot B is equal to B dot A. Again, the position doesn't matter here. Both are going to be equal. So this type of operation is the law called as cumulative law or commutative law. We'll just have a glance on different laws. Many things are there. So I think this class will go only for understanding these things. Then associative law. See, a plus b whole bar, sorry, in the bracket a plus b is one group plus c, and which is equivalent to the, where I am the bracket b plus b is one group here, adding with the c, which is equivalent to a plus the group of b plus c. So during the OR operation, wherever if we make a group, that does not matter in associative law. Okay, the value which is associated with this group along with this variable is same as the different variable and the different group when it comes to OR operation or AND operation. Okay, a dot b is one group, again it is product ANDed with c, whereas a dot with the group b dot c, the result will be same always. If you change the groups, the result will be same always. Okay, even this I can write it as a dot c dot b. Only the groups association is being changed here, but the association, that is what is called as associative law, where different variables are associated with each other with a different another variable, but still the result is always same. So another 5 minutes or 10 minutes is remaining for this class. We will just finish another three things are there. We will sign. Next one, distributive law. So whereas a distributive law, see, a dot b plus c is equal to a dot b plus a dot c. Simple. These are main basic rules of mathematics, right? So here b plus c is being distributed to a as a dot b and a dot c. If I go for a plus b dot c dot z, then a plus b dot a plus c dot a plus z. It is just a distribution of variables along with other variable groupisms. Then absorption law. So whereas absorption law, see, a plus a dot b. Now here a is the same thing what already one variable is there. So where we will get the value a only. If I go for a plus a dot b or a dot a plus b, both are opposite to each other. Wherever or is there and we have put, and is there or we have put, but always output is a for these types of expressions. So how that we will get? Say suppose a is 0 for this, a is 0 plus, say consider a is again 0 here, dot b is there, b may be anything, b may be 0 or 1, but what will happen here, b dot 0 is 0, 0 plus 0 is always 0. So whatever the input was there a, the same thing I have got here. Say for example, I'll take it 1 here plus a is 1 dot b. B may be 0 or 1. Let us not bother about that. If b is 0, 0 dot 1 is 0. 0 plus 1 is again 1. If b is 1, 1 dot 1 is 1. 1 plus 1 is again 1. So whatever this input is there, that is reflecting at the output side. So this value is absorbing this one, right? This, the second term, second value, second variable has been absorbed into the first value here. So a plus a dot b is equal to a, and a dot a plus b is equal to a only. If we prove, the same thing we will get. And a and b either may be 0 or 1. That doesn't matter. So this is absorption law. And then idempotency property, whereas a plus a is always a dot a is always a. I don't think this has to be proven. Okay, a plus a, 1 plus 1 is 1, 0 plus 0 is 0, 0 dot 0 is 0, and 1 dot 1 is always 1. Next, De Morgan's theorem. This is most important in all other theorems, from all other theorems. Okay. So here, a plus b whole bar is always equal to a bar dot b bar. See, now here the plus is there and whole bar is there. When I divide this bar, then the plus is converted into dot. When I divide the bar, a plus b whole bar, I will divide the bar now. It means a bar and b bar. Now here plus is replaced, that is or is replaced with the and function when I divide it. Okay, and this is one rule, and another rule is, that is the same thing, a dot b whole bar. Now in between these two variables, the operation is dot function. And now when I divide the whole bar into individual variable, then the dot is replaced with or function, plus function. Okay, now it is a bar plus b bar. So these are the two rules, two De Morgan's theorem rules, right? Which can be defined as the complement of sum. See, the complement of sum, this is the sum, no? Plus is a sum. The complement of this sum is equal to the product of their individual complements, right? There is a product and there is an individual complement, a bar and b bar, individual complements. The same thing in the second rule, second De Morgan's theorem. The complement of product, see, x dot y dot z whole bar is equal to sum of their individual components, x bar plus y bar plus z bar, or a dot b whole bar equal to a bar plus b bar. So whatever the whole bar is there, when it is being divided, and when it is being divided into an individual variable complementary, then the function changes from summation to dot matrix, that is product, and from product to sum. So this one again we will continue in the next class, this De Morgan's theorem, and whatever the things are there in the next we will see, and then we will go for Karnaugh map, K map solutions. So we will close the class now.